Albert Einstein's theory of special relativity implies that as you speed up, you will seem to be stuck in slow motion relative to other observers. This is called time dilation, and it is easy to understand with a constant speed, so constant time dilation. This is known as an inertial reference frame because its speed is constant. Another part of Einstein's theory states that all inertial reference frames are equal. Any observer moving at a constant speed can't do any test to prove that they're moving. Their perspective is equally as valid as anyone else's. With these two parts of the theory of relativity, we can construct a paradox. This paradox is called the twins paradox. It goes like this. There are a pair of twins, and one of them travels away from Earth near light speed, then comes back. After the trip, the twin that stayed on Earth calculates that because of time dilation, the traveling twin should be younger than him. The traveling twin, since his reference frame is just as valid as the stationary twin's reference frame, calculates that he is in fact older while his brother is younger. When the traveling twin comes back to Earth, however, he is in fact younger, as the stationary twin calculated. But why does it work out like this? What makes stationary twin correct? There are a few factors that make this problem more complex than it seems. First is length contraction. In the setup of this paradox, we only acknowledge time dilation as a relativistic effect, but really length contraction is present too. In fact, since length contraction and time dilation have the same equation, the Lorentz factor, they match each other. The stationary twin calculates the traveling twin's shorter time because of time dilation, while the traveling twin thinks that his trip itself is shorter because of length contraction. As a result, both twins agree on the duration of traveling twin's journey. However, traveling twin thinks that time dilation and, although he doesn't realize it, his own length contraction are acting on stationary twin. So, he thinks stationary twin's duration is even shorter than his. The way we fix this discrepancy in stationary twin's duration is by acknowledging the fact that traveling twin is not on an inertial reference frame. He is on two. This switch in direction here makes traveling twins switch inertial reference frames. If you make a world line graph, you can see the continuous view of these two frames. The outgoing frame thinks that it takes a shorter amount of time to get from the stationary frame to the ingoing frame than the stationary frame thinks. Then, as the outgoing frame continues, he thinks that it would take a long time for the ingoing frame to get back to the stationary frame and end the traveling twin's trip. The ingoing frame sees the opposite. The start of the trip took a long time and the end was short. Traveling twins' trip is a combination of the short parts of both frames' trips. Of course, traveling twins' instantaneous switch in direction can't happen. He needs acceleration. If you graphed acceleration, it would be interpreted as an infinite number of reference frames. Pieced together, traveling twin's perspective of stationary twin looks like this. Stationary twin is in slow motion because of time dilation, then the reference frame changes cause him to speed forward. Finally, time dilation slows him down again. Remember, while it may look like acceleration caused the speed forward of stationary twins' time, it is really the result of reference frame change. Because if you looked at an isolated reference frame, you would get similar results. In conclusion, the twins paradox is not a paradox. The traveling twin agrees that his trip is shorter, so when he comes home, he is younger.